Hi everyone, I am Vipin Kumar and I welcome you all to IIT and GATE classes. So in this series of GATE 2023 Mechanical Engineering paper solution, in this session we are going to focus on the thermodynamics part, which is both basic and applied thermodynamics. Okay, so without any delay, let us start. Okay, so let us see. So we are going to focus on technical part, and as I said, we are going to be focusing on basic thermodynamics plus applied. Okay, applied thermodynamics. So I have made a combination of all the papers, all the questions that has come from all from these two topics. And so let us go to the first question. So this question came from power plant. Okay, this was a power plant question. Now let us read the question line by line, and then we'll try to understand and we will try to solve this question. So what does the question says? It says consider an isentropic flow of air. So basically the fluid that is entering here is air and the flow is isentropic, okay, to the duct. And we see the duct here, and gamma is 1.4. This is your gamma is equals to 1.4 shown in the figure. The variation in the flow across the cross section are negligible. Okay, now the flow condition at the location 1. So let us say location 1 is inlet and location 2 is outlet. Okay, now so the duct cross section area at location 2 is given as twice of cross sectional area at 1. Okay, so it is a diverging section, right? It is a diverging section where A1 denotes the duct cross sectional area at location 1. Which one of the following is true? So if we see the options, there is a relationship between velocity, inlet and outlet velocity, and inlet and outlet pressure. Okay, now at the first instant, if you see this section, okay, it is a diverging section, right? It is a diverging section. And at the first instant, if you look at it, how does it look like? It looks like a diffuser, we all know, right? It looks like a diffuser. And if you see this kind of cross section, that is converging cross section, right? This is your inlet. This is your outlet. Again, this is your inlet. This is your outlet. So this is how the fluid is flowing here also and here also. Now again, it looks like a nozzle, but there is a catch here. What is the catch? You cannot just judge it based upon the section diverging or converging. There is a parameter called Mach number, which will tell you how this cross-sectional duct is acting. Okay, so I hope you all know this. What do you know? That if just one second, okay, if Mach number is less than 1, if this Mach number is less than 1, so basically we are going to define the Mach number at inlet, and if the Mach number is less than 1, this entry that is happening here is happening at subsonic condition. Okay, entry will be subsonic. So when it is subsonic, it is going to act as a diffuser. Okay, it is going to act in a normal way. So how it seems, it is going to act in the same way. So that means this duct will be a diffuser. It will be a diffuser. Now if you see this section, and it is acting as a diffuser, based upon the Mach number, then what will happen with velocity and pressure? Velocity, of course, is going to decrease. Velocity, yani ki U2 will be less than U1. Velocity is decreasing, and what will happen with pressure? P2 will increase. P2 is greater than P1. This is when the Mach number is less than 1. Now if the Mach number is greater than 1, then the situation is opposite. Okay. Now how, even if it is a diverging section, but because the entry will be supersonic. Okay. Now if the entry is supersonic, what is going to happen? It is going to behave in the different manner. So this duct will now act as a nozzle. And what happens in a nozzle? What happens in a nozzle? Velocity increases. That means U2 will be greater than U1, and pressure decreases in a nozzle, of course. So P2 will be less than P1. So the whole answer, the whole solution is based upon what is the Mach number here. So the most important criteria here is to determine Mach number, and based on that we will be able to determine the relationship between velocity and the pressure. Okay. Okay. So let us try to determine Mach number. Mach number is given by velocity. So we are talking about inlet condition. Okay. So inlet condition. So inlet is velocity is what? U1 and under root gamma R. T1 again inlet temperature. Okay. Now what is velocity? Velocity is 400 meter per second. You see inlet velocity. Inlet velocity is 400 meter per second. Okay. Now gamma is also given. Gamma is 1.4 and air is the fluid. So what is R for air? R is equals to 287 joule per kg Kelvin. Temperature is not known. Temperature is not known. So we have to find out temperature. Okay. So divided by gamma, which is 1.4 into 287 into T1. Now T1 is unknown. This is unknown. I need to find out T1. How do I find out T1? Now we know it is air, right? What do we know? It is air. And air behaves as an ideal gas. It can be approximated as ideal gas. So I can apply ideal gas equation at inlet, of course. So P1 V1 is equals to M R P1. I can also write this as P1 is equals to mass upon volume. So density 1 R T1. Okay. So I need to calculate T1. T1 is equals to density at inlet and R. Okay. Now what is pressure? Pressure was given as 100 kilopascal, I think. Okay. So P1 is given as 100 kilopascal and density is given as 1.2 kg per meter cube. Kg per meter cube. So it is 100 kilopascal. Density is 1.2 kg per meter cube. And R, just now I told you R is 287 in joule per kg Kelvin. But because the pressure is in kilopascal, I need to put my R as well in kilopascal. So 0.287 kilojoule per kg Kelvin. So if I solve this temperature, I will get around 290.36 Kelvin. Okay. I will substitute this P here and I will get what? Into 290.36. And if I solve this Mach number, if I solve this, I will get Mach number is equals to 1.171. And what it is telling me, that Mach number is greater than 1. Mach number is greater than 1. So which scenario is valid here? First scenario, A scenario, or B scenario? Of course it is B scenario. Okay. Of course it is B scenario. Okay. So when B scenario is valid, what is the relationship between velocity and pressure? This is the relationship between velocity and pressure. So U2 is velocity is increasing, that means U2 is greater than U1, and pressure is decreasing, that means P2 is less than P1. So let us see the options. So first one is saying U2 is less than U1. Yes, that is correct. U2 is, U2 is greater than U1. So this is not correct. This is not correct. Second option, U2 is less than U1, again, because it is nozzle. Okay, it is working as a nozzle. So velocity is going to increase. Third option, U2 is greater than U1. Yes, that is correct. What about pressure? Pressure is decreasing. P2 is less than P1. So of course that is correct. What is the next option? U2 is greater than U1. Yes, correct. And P2 is greater. So no, pressure is not increasing. P2 will not be greater than P1. So this is also not correct. Okay. So the right option is, correct answer is C. Answer is option C. Okay. Now let us move on to the next question. Okay. Now next question, very easy question, 1 mark question, okay, from thermodynamics. Which law? Second law. Okay. And let us read the question and try to understand what it is saying. So a heat engine extracts heat QH from a thermal reservoir at a temperature of 1000 Kelvin. So what is this? This is your higher temperature. Okay. And it is rejecting heat QL. This is the heat rejected by the heat engine at a thermal reservoir at temperature 100 Kelvin. So what is this? This is your lower temperature. Yes. Now, while it is producing some work as well, of course, it is a heat engine, it is going to produce some work. Now, they have given a relationship between higher heat transfer, lower heat transfer, and work. And we have to see which option is correct, which of the combination is correct. Okay. Now, so let us try to draw this question, draw the diagram of a heat engine. So it will be easier for us. Okay. Now, let us see. Look. This is a high temperature reservoir, right? T higher is given as 1000 Kelvin, and it is supplying some heat QH to a heat engine. This is my heat engine, and this is producing some work output. Okay, and some heat is also rejected at low temperature. QL is rejected at what temperature? TL. And how much is TL? 100 Kelvin. 100 Kelvin. Now they are asking us about a relationship between QH, QL, and W. Now, how do we get a relationship between QH, QL, and W? Well, we have first law of thermodynamics, isn't it? What is first law of thermodynamics for a cycle? Anyone remember the first law of thermodynamics for a cycle? It is energy in is equals to energy out. Now, if I talk about energy in is equals to energy out in terms of this heat engine, then what is the energy that is going in? What is the energy that is going in? So energy that is going in is QH. What is going in? Only this is going in and this is going out. This is going out. So can I write this as QH is equals to Q lower plus W? Yes, I can. Okay. So this is one condition. What is the second condition? What is the second condition to justify a relationship between QH and QL? Second law of thermodynamics. And what in second law of thermodynamics? Clausius inequality. Clausius inequality. For a cycle, of course. Okay, because for a process it is different. For a system it is different. Okay. So for a cycle, what do we have? We have cyclic integral of dq by t is always less than or equal to 0. If it is reversible, it is equal to 0. If it is less than 0, that means it is an irreversible cycle. Okay. Now again, in terms of this heat engine, how can I write? Can I write QH by temperature TH. It is positive because it is going inside. It is heat transfer to the engine. And then I can write minus QL by TL is less than equal to 0. Why? Why minus QL? Because it is heat rejected by the engine. It is heat rejected by the engine. Okay. So basically we have to check all our options based on this criteria. Okay. Now let us see. Option A. Option A, if we check. So QH is 2000, QL is 500, and this. So let us apply the first law. Let us apply the first law. Okay. QH will be equal to QL plus W, right? So can I write 2000, which is QH, is equals to QL is how much? 500, right? And W is how much? 1000. 1000. Now, is it equal? No. So this is not equal. That means your first law is not valid. So this is your invalid condition. That means first option is not correct anyway. Okay. Let us go to the second option, B option. What is it? QH 2000 will be equal to, by QH will be equal to QL plus W. How much is QH? 2000 is equals to 750 plus 1250. So that makes sense. That is correct, right? So can I write 2000 is equals to 750 plus 1250? Okay, this is valid then. Yes, this is valid. It is equal. Now we have to check the second condition. We have to check the second condition. What is second condition? This condition. How do I check this? So QH, which is 2000 by higher temperature 1000 minus QL. So QL is 750 upon TL is 100. So this is 2. It is equals to 2 minus 7.5, and it is 5 minus 5.5. That means my cyclic integral of dq by t for this particular combination is less than 0. So this is also valid. So you see option 2, both the conditions are valid. For option B, both the conditions are valid. Okay. Let us see option C as well. C option. So 6000 is equals to 500 plus 5500. That is correct. So our first law is valid. Okay. So it is saying 6000 is equals to 500 plus 5500. Valid? Yes. What about second law? What about second law? So 6000 by 1000 minus 500 by 100. Now it is 6 minus 5, which is equals to 1. So that means in this condition, cyclic integral of dq by 2 is greater than 0, which is impossible. It cannot happen. So it is invalid. And that means our option C is also not valid. Option A was also not valid. Okay. Now let us see the option D. D option. 600 is equals to 6000 is equals to 600 plus 5500. Is it valid? No, it is not valid, of course. So it is saying 6000 is equals to 600 plus 5500. It is not valid. It is invalid. The only option in which both the condition, first law and second law, is satisfied is option B. And therefore, my correct answer is B. Correct answer is B. Okay. I hope it is clear. Okay. So option B is correct. Okay. Let us move on. Let us move on to the next question. Okay. Again, this is 2-mark question, 41. Okay. Although very easy question. Now, which of the following statement is false? The focus here is we have to find out which one is false, not true. So 3 options will be True, one will be false. You have to find out which one is false. Okay, let's see. For an ideal gas, the enthalpy is independent of pressure. So many times we have solved this, so many times. For an ideal gas, I can write, here I can write option A. For an ideal gas, always ideal gas, internal energy is a function of temperature only, and enthalpy is a function of temperature only. That means A option is correct. We are not finding correct option. In fact, A is true. We are not finding true. We are finding false. Okay, so this is true. Okay, so this is not the correct answer. What about B? For a real gas going through an adiabatic reversible process. Okay, so what is adiabatic reversible? Isentropic process. The process equation is given by PV gamma is equals to constant, where P is pressure, V is volume, and gamma is the ratio of specific heats at the constant of the gas at constant pressure and volume. So can you tell me, is it correct or no? Is it correct or no? So you have to understand that real, because they are in the option they are giving real gas. So real gas do not follow. This is the ideal gas equation. You see, this is an ideal gas equation for isentropic process. This PV gamma is equals to constant. Okay, so this is the ideal gas equation, and real gas equation don't follow ideal gas equation. Okay, they follow equation of state, for example van der Waals equation and other equations as well. Okay, so option B, this is false. Okay, this is true, this is false. So till now my option B seems to be correct. Okay, let us move on to option C. For an ideal gas undergoing a reversible polytropic process, ideal gas is there first of all, and polytropic process is there. PV gamma 1.5 is equals to constant. So we know PVK is equals to, or PVN is equals to constant. So K is equals to polytropic index. Okay, and it is an ideal gas equation for polytropic process. Now the equation connecting the pressure, volume, and temperature of the gas at any point along the process is this. So this is my generalized ideal gas equation, and it is followed by all the processes, whether it is constant pressure, constant volume, isothermal, adiabatic, or polytropic. Okay, so all the ideal gas equation, which is PV is equals to mRT, it is followed by any ideal process. It is followed by any ideal gas. Any ideal gas can follow this equation. Okay, so that means it is true. Okay, option D, let us see. Any real gas behaves as ideal gas at sufficiently low pressure or sufficiently high temperature. That is the condition. That is a condition, that is an absolute condition when real gases behaves as ideal gas. When the pressure is low, when pressure tends to 0 and temperature tends to 2 times. Okay, it is greater than 2, reduced temperature. Okay, so when, I hope you remember, reduced pressure tends to 0 and reduced temperature is greater than 2, then real gas behaves as ideal gas. So at low pressure and high temperature, real gases behaves as ideal gas. This is also true. The only option that is false is this one. That means B is my correct option. B is my correct option. I hope it is clear. It is crystal clear. Okay. Now let us move on to the next question. Okay, this is done. Okay. Now the question seems to be, a little bit complicated, but it is a very easy question. If you are able to understand the question, you read it properly, and if you understand the question will be solved in one line. That's all. Okay. Now let us see. Consider a fully adiabatic piston cylinder. Fully adiabatic. There is no heat transfer. Okay. Piston cylinder arrangement as shown in the figure. The piston is massless and cross-sectional area of the cylinder is A. the cylinder is A. So this area, cross-sectional area, if this is diameter D, area is A. Okay. So the fluid inside the cylinder is air. So we have air. Okay. With gamma being the ratio of specific heat, just normal terms. Okay. The piston is initially located at position L1. Okay. Piston is initially located at this point. Okay. And the pressure inside is P1, which is greater than atmospheric pressure P naught. So outside we have P naught. The stop S1 is instantly removed. You remove this S1 and then you have another stopper S2. Okay, instantly removed, and the piston moves to the position L2 where equilibrium pressure. When piston moves to this location, the equilibrium pressure is P2, which is again greater than P naught. Now the work done by the piston on the atmosphere, very, very important. What we have to find out, work done by the piston on the atmosphere during this process. Okay, some options are given. We'll see that. Don't worry. Now let us try to understand what it is saying. Let's see. Look, what do you have? You have this. You have this. 1 second. Okay. You have this cylinder. Okay. And you have air here. There is piston is located here by a stopper. Okay, what do we have? We have a stopper here. And we have one more stopper here. So inside pressure is P1. And what is the outside pressure? Atmospheric pressure. Here P1 is acting, okay? This side P1 is acting. And this side atmospheric pressure is acting, P naught. Okay? Now what do I do? So at this point of time, when I remove stopper S1, when stopper S1 is removed, when I remove this, piston will move against atmospheric pressure P naught, right? Only the pressure outside is P naught, right? Now, when I remove this S1, the piston will come here. The piston will come here and stop again, right? And still the outside pressure is P naught, right? So when the piston moved from position 1, let us say this is position 1 to 2, the only pressure that was acting by the atmosphere is P naught. It was working against the piston. So let me write it like this. Piston is moving against a constant pressure P naught from 1 to 2. When the piston moved from 1 to 2, the only pressure that was working against the air or against the piston was P naught. So basically, it is if I say work done by the piston on atmosphere, it is very important that you understand this terminology. I am trying to calculate the work done by the piston against what? Against atmosphere. So I can also rewrite it as work done against the constant pressure. Against, that means during this process 1 to 2, pressure is constant, right? Against constant pressure P naught, right? So I can find out work in a constant pressure process as what? By normal work done is PdV, but because pressure is constant, I can take out P naught outside, atmospheric pressure, and V2, final volume minus initial volume, right? And what is this? V2 minus V1. And the area is constant. So can I write P naught area L2 minus L1. So constant pressure, the piston is doing the work against the atmosphere is this, right? So this is my correct answer. Let us see the option. Let us see the options previous. Okay. So 0, no, of course not 0. Piston has moved, boundary has changed, so this is not correct. P naught, atmospheric pressure into area L2 minus L1. Of course it is correct. We have just calculated it. P1A L1 Ln by L2, no. And this is also not correct. It is basically the work done. It is a isentropic. It is the adiabatic process. So it is basically work done by the. If they ask work done by the gas, so it is work done by reversible adiabatic process. Okay. So this then it will be the correct answer. But they're asking work done by the piston, by the piston. So B option is correct. Option B is correct answer is B. Okay. I hope it is very clear. Now, let us move on to the last question, which came from thermodynamics. Let's try to read the question. Consider a mixture of two ideal gases X and Y with molar masses mx is equals to 10. So it is a molecular weight. Okay. So let us try to draw a diagram so that we will understand this. We have a cylinder or a piston or whatever. We have a container. Okay. And we have one gas, this one, molecules of one gas. And this is, let us say, X. Okay. First ideal gas X. And we have one another, gas here Y. These are molecules of Y ideal gas. There are two ideal gases, red and green. Okay. Now it is saying molar mass. Molar mass, that means mx is equals to 10 kg per kilomole. Okay. And my, molar mass of the Y gas, is equals to 20 kg per kilomole. Okay, it's not very clear. Let me Y I am talking about, and molecular weight of Y or molar mass of Y is 20 kg per kilomole. Okay. The total pressure of the container. So total pressure, that means inside the container, the total pressure by the two gases is 100 kilopascal. Total volume of the container, it means, is 10 meter cube, and the temperature of the content is 300 Kelvin. If the mass of the gas X in the container is 2 kg, that means it is saying if mass inside is 2 kg, then the mass of gas Y. So I have to find out what is the mass of gas Y. This is what I need to find out in the container, is in kg rounded off to one decimal place. I have to find out. Okay. And they are saying R. What is this universal gas constant? R bar. Take R bar as 8.314 kilojoule per kilomole Kelvin. Okay. So of course these are ideal gases, so we have to use ideal gas equation, right? So now tell me, can I use, we know this, PV is equals to MRT. Can I use this? No, I cannot use this. Okay, because R I don't know. It is, they have given ideal gas, but I don't know R. If it is air, I can take R, but I don't know which gas is there, so I cannot take R, because this R is specific gas constant, right? It is specific gas constant. If the gas is not given, I don't know what is the R. So what I need to use, I will use PV is equals to 10 RT. Now this is universal gas constant. This is universal gas constant. Okay. Now I know pressure, total pressure. Total pressure is 100 kilopascal. Volume also I know. N I don't know. N is what? Total. N here is total number of moles. Total number of moles. Which means N is equals to number of moles of X plus number of moles of Y. Okay. Now this is 8.314 into 300 is the temperature. So I can find N. Now N you will get as 0.4. Now what is N? N is equals to Nx plus Ny is equals to 0.4. Now how can you define number of moles? Now N is equals to mass by molecular weight. Okay, so I can write mass of X by molecular weight of X plus mass of Y molecular weight of Y is equals to 0.4. Now I know everything. I know everything except M mass of Y. So 2 kg is given, right? 2 kg is given. 2 upon 10 plus My upon what is capital My molecular mass of Y gas. It is 20 is equals to 0.4. So I can calculate mass of Y is equals to 4 kgs. Okay, so it should be around 4.0. Yes, it is exactly 40. So you can write 4.0 kg because they have asked from to one decimal place. Okay, the answer is My is equals to 4.0 kg. Okay, I hope it is clear. Okay, sure. So this was the last question that was asked from thermodynamics. And so how many questions came? If we talk, the first question is of 1 mark. Okay, 1 mark question. Again 1 mark question. So 2 marks in total. 2 mark questions. So total 4 marks. Okay. Again 2 mark questions. So total 6 marks. And again 2 mark questions. So total 8 marks. Okay. The total weightage of thermodynamics was 8 marks. Okay, I hope it is clear. The total weightage of basic and applied thermodynamics is 8 marks, which is basically 8% of the total gate marks. Okay, so it's a good weightage. It's a good weightage. Okay, so I'm going to wrap the session here, and we are going to meet at 3 p.m. like after 15-20 minutes, and we will solve the gate questions, gate 2023 questions of HMT. Okay, so I'll see you there. Thank you very much.